Hello everyone, this is Siswanto, and we are going to start 11.1. So chapter 11 is basically sequences, induction, and the binomial theorem. Now in 11.1 we will talk about the sequences in general. In 11.2 is arithmetic sequences and geometric sequences in 11.3. And mathematical induction in 11.4 and binomial theorem in 11.5. Okay, so let's now start with the sequences, which is 11.1. Okay, so as usual, you are going to take notes along with me. So have your paper and pencil ready, and we could start. All right, let me see. Good. So let's start. Share desktop. Okay, and I recorded already. Now, 11.1 is sequences. All right, so sequences. Yeah. What is a sequence? So A, let's label this. A sequence is a function that computes an ordered list. Okay, and the domain of this function is the set of all positive integers. The domain of this function is the set of all positive integers. So it starts with 1. So 1, 2, 3, 4, 5. Those are the domain. Okay. So so example of a sequence is example of a sequence. We could just have an easy example: 2, 4, 6, 8, 10, blah blah blah. Yeah, meaning the sequence goes on forever. Now this is when n is equal to 1. This is when n is equal to 2. N is equal to 3. Maybe I should write it. N is equal to 3. And here when n equals to 4. And this is when n is equal to 5. Yeah, so each of these are called terms. And when you say it's a function, well, let's define this function. So in this case, f of n is equal to 2n. So 2 multiplied by n. So 2 multiplied by 1 is 2. 2 multiplied by 2 is 4, etc. Yeah. And you know there's a formula, f of n is equal to 2n. And this goes on forever. So this is called an infinite sequence because it goes on forever. Yeah, it doesn't stop. 10, 12, 14, 16, etc., etc. Okay. So so we have what is called finite sequence. So a finite sequence. So this is a sequence that stops. So for example, 1, 5, 10, 15, 20, and it stops here. So it is called a finite sequence. Okay, and you also have an infinite sequence. So this is the sequence which goes on forever. So usually we use these 3 dots. It's called ellipsis, meaning it goes on forever. So for example, 1, 3, 5, 7, 9, etc. So these are ellipses, meaning these 3 dots, meaning it goes on forever. So this is an infinite sequence. Infinite sequence. So it doesn't stop, goes on forever. Yeah. So it goes on forever. All right, good. Now, let's write talk about the general term of a sequence. So the general term of a sequence usually has this form. So we usually use AN. So AN, or you could put a set notation is, for example, n plus 1 over n plus 3. Or I don't have to put the, the set notation, so I could just write an is n plus 1 over n plus 3. So we could start, yes. So we could list, yeah. So list the first 5 terms of an is equal to n plus 1 over n plus 3. So let's start with n is equal to 1. So we always start with n is equal to 1, yeah, not 0, yeah. So what is A1? A1 is, 2 over 4 is equal to half. And then A2, so n is 2, is 2 plus 1 over 2 plus 3. So this is 3 over 5. Now A3 is equal to 3 plus 1 over 3 plus 3. So this is 4 over 6, so this is 2 over 3. A4 is equal to 4 plus 1 over 4 plus 3. So 5 over 7. And A5 is equal to 5 plus 1 over 5 plus 3. So 6 over 8, this is 3 over 4. Yeah. So if you list the sequence in order, these are the first 5 terms, or you could write half, 3/5, 2/3, 5 over 7, and 3/4. But we stop here because that's what being asked. List only the first 5 terms. Yeah. Well, actually, the sequence an is equal to n plus 1 over n plus 3. This one goes on forever. Yeah. But we only need to list the first 5 terms. Okay. All right. Now let's do. So this is 1. Yeah. What about if we list another 5 terms, the first 5 terms of an is equal to -1 to the n over 2 to the n. So that's an. Yeah, this is the second an. Now, if we have a -1 raised to a certain variable here, most likely it will be just a sign, because -1 raised to an odd number is negative, and -1 raised to the even numbers are positive. So the signs will alternate. Yeah, so -1 to the n, if we have these, it means the signs will alternate. Alright, so let's write down what is A1. So A1 is -1 to the first over 2 to the first. So this is -half. Okay. Now A2 is -1 square divided by 2 square. So this is 1 over 4. So you see there's a sign change. Now A3 is -1 cube divided by 2 cubes. So this is -1 over 8. And A4, well, we could guess it will be positive, and then you know how you keep multiplying these by 2, the denominator by 2. So positive times 2, so 1 over 16. Or if you write the formula, that's fine too. A5, it will be negative, and then the top will be 1, and this will be, the bottom will be 3 over 2. So -1 over 3 over 2. Yeah. So if we write it in order, then we will have -half, 1/4, -1/8, 1 over 16, -1 over 32. So that's what we have. Yeah? Okay, good. Now, let's talk about convergent versus divergent series. Yeah? So, convergent series, convergent sequence. Yeah? Alright, so what is a convergent sequence? Um, so, a convergent sequence um, converges to a number at the end, yeah, when Sn become large. So convergent sequence, yeah, uh, is a sequence whose term converge um, to a number Sn becomes large. So to give an example of a convergent sequence is An equals to 1 over n. So we could list some 1 half, 1/3, 1/4, 1/5, 1/6, etc. So once n is bigger, when n is large, then this converges to 0. Yeah, so when n is large, when n goes to infinity, An converges to 0. So that's how we say it. So when n goes to infinity, An converges to 0. Yeah? So this is an example of a convergent sequence. So let's just give example of divergent sequence. So it goes without bound. Yeah, it's going to be bigger and bigger and bigger every time, or smaller and smaller and smaller and smaller every time. I mean, not smaller, but more negative and more negative, more negative, more negative. So it's called divergent sequence. Yeah. So to give an example of a divergent sequence, An is equal to n. Look at these. So it starts with 1, 2, 3, 4, 5, etc. Now when n goes to infinity, yes, An it also goes to infinity, right? That's called a divergent sequence. Yeah. So we talked about convergent. So the series whose terms converge to a number as n becomes large. So we're talking about the terms. Yeah. Okay. Now the next one, we will talk about recursive sequence and then the factorial symbol. Yeah. What is a recursive sequence? So a recursive sequence, so it's called recursive sequence, is a sequence whose terms are defined using are defined as an expression involving the previous terms. Involving the previous term. All right. Okay. So, for example, let me see. Yeah. So, example of recursive sequence. So this is divergent, this is convergent. Okay. Now, recursive sequence, so for example, A1 is equal to -3. And An is equal to 2n multiplied by a of n minus 1. So you see this term here is a previous term. Yeah. If n is greater than 1. Okay. So what do you do to it? You multiply the previous one by 2n. Yeah. Now let me copy this because we're going to write down a few numbers. So what are the elements or the terms of the sequence? So terms of the sequence. So the first one's -3. The second one is 2 times 2, so n is 2. So 4 times the a1. So 4a1 is 4 times -3. So this is -12. Okay? So 4 times a1. a1 is -3. So 4 times, so this is n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, etc. Yeah. So 2 times 2, so 2n, 2 times 2, times the previous term, so -8. Now the next one is 2 times 3, so 6 times the previous term. So 6 times -12 is -72. Yeah. Okay, so now the next one is when n is equal to 4. Yeah, when n is equal to 4. Alright. So 2 times n, 2 times 4, it's 8. 8 times the previous term. So what will this be? Is it going to be -576? Okay, etc. Yeah. So 72 times 8, so 56 and 16, yes, -576, etc. Yeah, this number's a little bit big. Okay, but you guys get the idea, right? This is a recursive sequence. It's based on the previous term. Now the other thing is Fibonacci sequence. That is also an example. Yes, well-known example. So another example would be a Fibonacci sequence. What is Fibonacci sequence? So it says that A1 is equal to 2 and A2 is equal to 3 and AN is equal to AN minus 1 plus AN minus 2. So you're adding the previous two terms. This is called a Fibonacci sequence. Yeah. So if n is greater than 2. Okay? So now, so here are our terms for Fibonacci sequence. 2, 3, and then it says that the fourth one we will add these two. So 2 plus 3 is 5. Now the next one we will add this one, 8. And then the next one we will add this one, 13. The next one, 21. Alright, so these are the terms of Fibonacci sequence. Okay, so it's defined recursively. It involves the previous term. So in this case, it involves 2 of the previous terms. Okay? Alright. Now, we also will talk about the factorial symbol. So, we still have this factorial symbol. So that is n factorial. Yeah, this exclamation mark here, it's factorial. So what is factorial means? Yeah. So this 0 factorial is defined as 1. 1 factorial So here n greater than or equal to 0. So we're not talking about negative 1 factorial. Okay? 1 factorial is 1. And what about the others? So let me see. An. So what is n factorial? So n factorial is n times n minus 1 times n minus 2 all the way till 3 times 2 times 1. So this is when n is greater than or equal to 2. Yeah. So for example, what is 3 factorial? So this is just 3 times 2 times 1. So this is 6. What is 7 factorial? So this is 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? So this is 6 times 4. 6 times 4 is 24 times 5. So 20 times 6, 120. 120 times 6 is 720. 720 times 7, well, what's that? Let me get my calculator really quick. Okay. Okay. So we're multiplying out everything. Okay. So what did I say here? This is 6 times 20 is 120 times 6. So 120 times 6 is 720. 720 times 7. Let me see. So 720, 720 times 7. It's 5,040. Yeah. But if you see here, I could also write 7 factorial is equal to 6, is equal to 7. So it's equal to 7 times 6 factorial. Why? Because all of these is 6 factorial. Yeah. So we could also write n factorial as n times n minus 1 factorial. Yeah. Okay. Good. So we talk a little bit about factorial, of what factorial means. Yeah. So the exclamation mark. Okay. So now B, we're done with sequence. So now we will talk about series. Series, okay? So what is series? A series is the summation. Let me see here. Use summation notation. Series. Yeah. So series is adding up all the terms. Okay. So suppose I have a sequence. So we're talking about sequence first. So the sequence is an is equal to 1 over 2 raised to the n minus 1. So in this case, when you list the terms, the sequence would be 1, half, 1/4, 1/8, etc. Right? So that is the sequence, yeah, of an equals to 1 over 2 raised to the n minus 1. Now, what is the series? So S1, so series is the sum. So S1 is just 1. Now S2 consists of the sum of 2 terms. So 1 plus half, which is 3 over 2. Now S3, so we're adding up to the third term, is 1 plus half plus 1 over 4. So S3 will be 3 over 2 plus 1 over 4. What is 3 over 2 plus 1 over 4? So 6 over 4 plus 1 over 4, that is 7 over 4. So S4 is 1 plus half plus 1/4 plus 1/8. Yeah. So we know what this is. This is 7/4 plus 1/8. So we have 14/8 plus 1/8. So that's 15/8. All right. Yes. So let's talk about the difference between sequence and term. So sequence are just numbers, a list of order, and then it's listed in this order: A1, A2, A3, all the way up to AN. So that's your sequence. What about series? So I'm going to write it as Sn. So this is a finite series. Yeah. So Sn is equal to A1. So it's up to n term plus A2 plus A3 all the way up to AN. So this is called a finite series. Okay. And there is a summation notation here. So there is a summation notation is sigma. So sigma indicates summation. AI, because we're using A1 plus A2 plus A3 up to AN. So this is I goes from 1 through, when does it end? So it's A1 blah 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 up to AN. So I goes from 1 to N. So this is again sigma. So Sn is I equals to 1 from 1 to N of AI. Yeah, this is a finite series. Yes, so it ends at one term. Yeah. Now this is finite series. Okay. Now the second one is infinite series. Okay. So S of infinity, I mean it is infinite. So this is equal to A1 plus A2 plus blah 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 plus AN plus, we don't know. So this is, how do we write it as a sigma notation? So sigma, I goes from 1 through infinity in this case. So yeah, is AI. Alright. So this is, the symbol is called sigma. And it signifies addition. Yeah. And then what is I? I is the index of summation. Alright. So I is the index of summation. Okay. Alright. Let me see. We were going to do number 71 till 74. Oh, actually, that has to be done a little bit later. Yeah? Okay. So now, let's talk about the summation properties and summation rule. Give me a second. Give me a second. Yes. Sum of sequence. Yeah. Series is sum of sequence. So a series is a sum of a sequence. Yeah. Okay, let me see. Summation property. So sigma is signify the summation. Now let's write down the property, yeah, of summation property, of the sigma property. Alright. So let's write these. So C, properties of sequence. Okay. So what is of sequences? The first one is, so sigma I goes from 1 to n. So this is how many times? Of C, oh, what am I doing? C is equal to what? So in this case, you're adding C plus C plus C up to how many times? N times. So what is N times C? So this is NC. So sigma I goes from 1 through N is equal to NC. All right. Good. Now, the second one, number 2. What is, oh, okay, I'm sorry. I should put AI here. AI. So CAI, CA1, CA2, CA3, okay? So this is equal to, I'm sorry, I'm referring to a different one here. So sigma I goes from 1 through N CAI. This is equal to C times sigma I goes from 1 through N AK. So this is a constant. We could take the constant out of the sigma summation notation. So let's write that. Let's write that down. So let me write this again. So C times A1 plus C times A2 plus C times A3 plus up to C times AN. Yeah? All right. So we could factor out the C. C is a constant. Okay? So that's the first one. Now, if I'm adding AK, this is a sequence, plus BK, this will just distribute. So this is equal to I goes from 1 through N AK plus sigma I goes from 1 through N BK. Yeah. All right. And it's also true for subtraction. AK minus BK. So in this case, this is sigma I goes from 1 through N AK minus sigma I goes from 1 through N BK. So plus or minus. All right. And also, what if the summation index doesn't start at 1? So for example, if I have I goes to is equal to, okay, I goes, oh, AI. I'm using I, not K. Here maybe I use K. Yeah. So K is equal to J plus 1. So through N. And it doesn't start with 1 of AK. So basically what we do here is we start everything from 1. K goes from 1 through N, AK, and then we have to subtract. K goes from 1 through J of AK. Yeah, so you have to subtract the first few terms here. Yeah, because K doesn't start with 1. Alright? Okay. Good. So those are the properties of sequence. And let's write down the formula for the sum of sequence. Yeah. Okay. Let me see. Summation rules. Summation rules. So number 1, sigma K goes from 1 through N of C. So this is equal to, this is what I was writing before, C plus C plus C How many times? N times. Because you're calculating since 1, 2, 3, so n times. So this is equal to n times c. Alright? So c is a constant. What about if I have sigma k goes from 1 through n of k? So this is 1 plus 2 plus 3 plus blah 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 plus n. So this is basically n times n plus 1 divided by 2. Okay, so the difference between k and c is this is a constant. It's not related to k. Well, this is a k. So k is 1 and then 2 and then 3. Alright. Anyway, the third one, what about if I'm adding k squared? So this is 1 squared plus 2 squared plus n squared. So k goes from 1 through n. So this is equal to n times n plus 1 times 2n plus 1 over 6. That is the formula. Yeah? Okay, so 1, 2, 3. Now the next one, what about cube? So this is goes to n. So sigma, what am I writing here? This is n. Sigma k cube. So k goes from 1 through n. So this is 1 cube plus 2 cube plus n cube. This is actually the same as the second formula here, but square. So it is n times n plus 1 over 2, but square. We square it, so a little bit different. Yeah. If you memorize it, it is good. Yeah. You may not need it all the time, but for this chapter, you need to memorize. Yeah, the formulas. Okay. So here you're adding 1 plus 2 plus 3 plus n. That's n times n plus 1 over 2. Good. Alright, so let's do some example. Yeah. Let me see some example. What about if I have these? So for example. Evaluate Alright, so number 1, sigma I goes from 1 through 5, 4i squared minus 2i plus 6. Alright. Maybe let me do it on a different page. So let me copy this and then start it on a different page. Yeah? Okay. Alright. Evaluate this. So this is, we can rewrite this. This is 4 times the, now the 4 is a constant. I could just take it out of the, what is it? Summation notation. So 4 sigma I squared minus 2 sigma I plus sigma 6. Yeah, so now we will write the index. I goes from 1 through 5. And then this one also goes from 1 through 5. Alright, so what is this? And I'm using the formula, right? So the 6 sigma I squared will be n times n plus 1 times 2n plus 1 all over 6. So that is sigma I squared. Yeah. So here this is 4. So n will be equal to 5. So n times n plus 1. So what is n in this case? N is the upper bound. So n times n plus 1. N plus 1 is 5 plus 1. So n, oh, I didn't write the n. Yeah. So 4, and maybe we should write it first. Yeah. So sigma I square is equal to n times n plus 1 times 2n plus 1 over 6. And sigma I is equal to n times n plus 1 over 2. I think it will be easier if we write it down. So in this case, n is 5, so the first one would be 5 times 6 times 2 times 5 plus 1, so 11 divided by 6. Alright, so this cancel. So this gives me sigma I square. Yeah, so n times n plus 1 times 2n plus 1 divided by 6. Okay, so in this case, n is equal to 5. Yeah, so probably we should write down here. So this is your n. Yeah, n is equal to 5. Okay? Now, minus 2 times sigma I. So sigma I is n times n plus 1 over 2. So 5 times 6 divided by 2. So actually this one cancel. Yeah. Plus, I goes from 1 through 5, 6. So in this case, it will be 5 times 6. Alright, so what is this? Let me see. So this is 4 times 55. So is it 220? So 4 times 55. Yeah, that is 220. Yes. Minus, what is this, 5 times 6? 30 plus 5 times 6, that is 30. So let's check again. This is 2 times 5 times 6 divided by 2, yes. So this is just 6 times 5 times, yes. So this cancels, so equal to 220. Okay? Let me see what else I am missing. Oh, okay, something number 71 to 74. Let me see, what is that? Okay. What about number 2? This is sigma k goes from 1 to 40 of k. Alright. So basically, this is 1 plus 2 plus blah 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 plus the last one is 40. So 40 terms basically. Now if we use the formula, we will use this formula. Okay. So this is equal to n is 40 times 41 divided by 2. So this is actually 20 times 41. So this is equal to 820. Yeah. So sigma k is 820. Good. Now, what about if I have, let me see, number 3, because we did number 1, which is already difficult. Why don't we use different index here? So for example, what is sigma k goes from 10 to 60 of 2k. Alright? So it doesn't start with 1. So basically, what happens to the 1 through 9? Yeah, it's subtracted. So this is the whole set. K goes from 1 through 60 of 2k, right? And then we will subtract the first 9 terms. So this is divided by 2 here. Then we will subtract the first 9 terms. So k goes from 1 through 9 of 2k. Now we could easily solve these. K goes from 1 to 60 of 2k. So 2 times, what will this? Which one formula? N times n plus 1 over 2. So n is 60 times n plus 1, 61, divided by 2. So you have to cross this out, right? Minus 2 times k. K goes from 1 through 9. Again, this is 9 times 10 divided by 2. Alright. So what is this equal to? 60 times 61. What is that? 6 times 61? 3660? Yes? Okay, 60 times 61, 3660. Minus, what is this? 90. So it is 3570. Yes. Yeah. All right. Let's do one more. Number 4. Okay. So in this case, these are my n. Just in case you are wondering, what are the n's? These are all the n. So this is n. This is n. N is the upper bound. Yeah. And this is n. So in this case, this is your n also. Okay. Now number 4. What is sigma k equals to 4? K goes from 4 to 24 of k cubed. Well, then again, what we do here is this one doesn't start with 1. So we will do a series that starts with 1 through 24. And then this is k cubed. But we have to subtract the first 3 terms, right? Because it starts at 4, we have to subtract the first 3 terms. K goes from 1 to 3 of k cubed. So what is the formula for k cubed? So sigma I cubed. It is n times n plus 1 over 2 square. That's his formula for sigma I cubed. So this is going to be, this is your n here, and this is your n here. So 24 times 25 divided by 2 square. That's sigma k cubed from 1 to 24. Minus, let's subtract the first 3. So 3 times 4 divided by 2. And then we square this. Well, what is this? This seems like a very big number. So this is 12. 12 times 25, isn't it 300? So 12 times 25. Yeah, it's 300 square, so 90,000. So 300 square is 90,000 minus, what is this? This is 2. 6 square. 6 square is 36. Alright. So 90,000 minus 36 is 899. Let's see, what is this? 64? Yes. So 89,964. Okay? Alright, so we will end the discussion here, and tomorrow we will start with 11.2, which is arithmetic sequence. So for today, there's just sequence in general. So what we did was we defined what sequence is, what series is, which ones are like terms, which one what else did we do today? Recursive sequence, yes, and then we evaluate the formulas, yeah. Okay, guys, I guess we should continue next time with the other sections. We're done with 11.1. Okay? All right. So let's see here. We will finish. We are finishing. We finish 11.1, which is sequence. Okay? So I guess we will see you later. Then let me stop the recording now. Yes?